So, good morning, one and all. So, let us start today's class. So, that is representation power of a multi-layer network of sigmoid neuron. So, if you remember, in the last classes, we have seen the representation power of a multi-layered network of perceptron. This. There, what we have studied, a perceptron with a single hidden layer can represent any Boolean function with no errors. An MLP with a single hidden layer can be used to represent any Boolean function. Here, the Boolean function can be linearly separable or it may not be linearly separable. So, all Boolean functions can be represented with a MLP having a single hidden layer. And here, there are no errors. Without errors, we could able to represent all Boolean function using MLP. But what about the multi-layer network of sigmoid neurons? Now here, the representation power of a multi-layer network of a what now? Sigmoid neurons. What it says? A multi-layer network of neurons with a single hidden layer can be used to approximate. Here remember, it is approximation, not the exact representation. Any continuous function. Okay. So, using sigmoid neuron, you can approximate any continuous function to any desired precision. Okay. So, what is the difference between these MLP and sigmoid neuron? Using MLP, you can exactly represent all Boolean function with no error or without error, with precision. But here only Boolean functions. So, using sigmoid neuron, you can represent or you can approximately represent any continuous function. Here it need not be Boolean to any desired precision, which means we can tolerate some errors. Here you may not get zero errors. You may get some errors which are in the tolerable limits, and you are representing a continuous function, and that is approximately. This is the representation power of a sigmoid neuron. Obviously here also we are having only single hidden layer just like MLP. Okay, the difference is it used to represent continuous function and it can have some tolerance, some precision, desired precision, and it is approximation. These are difference between the representation powers of MLP and sigmoid neuron. Now this is called universal approximation theorem. What it is called? Universal approximation theorem. What it says is, in other words, there is a guarantee that for any function from Rn to Rm, we can always find a neural network with one hidden layer containing enough neurons whose output g of x satisfies this one. Okay. So, what they want to say is, so we have a neural network, input is x, output is f of x, that is simply y. Now, we have a prediction that is g of x, that is simply y cap. So, y is the actual output or true output, y cap is the what? Prediction. Now, so what is this? Mod of f of x minus g of x is less than or equal to epsilon for all x. What do you mean by this? What is f of x? Y. What is g of x? Y cap. Which means the difference between the true value minus true value and the estimation is less than or equal to epsilon. Which means now this is the error actually. What they want to say is the error is within the error is less than or equal to epsilon. Now this is the desired precision or accuracy, which means we are not getting zero errors, but the error is very, very minimum, bare minimum. How much? Epsilon. So we can design this parameter epsilon. We can choose that parameter, which means, so what they want to say is, we can always find a neural network with one hidden layer containing enough number of neurons. That is also very, very important. Whose output g of x satisfies for all input x. Okay. So using a neural network containing one hidden layer, and that layer contains enough number of neurons, using that we can represent any function with a desired precision like this. Now what is this function f of x? It is from Rn to Rm. So these are number of inputs, this is the number of outputs. Okay. Now this is called universal approximation theorem. What exactly it means is, using that, this is the theorem, you can read if time permits. You can compute any function. That is a universal approximation theorem. What it says is, you can compute any function. Any continuous function. So the ability to compute arbitrary function is remarkable. Okay. So these are some examples. So example is translation of a Chinese text to English. Okay. Suppose you have a Chinese text, so that can be translated to English. So this is the problem we have, or this is the function. So this can be solved by using a neural network. Okay. So like this we have so many problems. They can be solved by using a neural network containing single hidden layer and having enough number of neurons with a desired precision epsilon. Is it okay? Right. Now, so now let us go to the universal approximation theorem. So this is the link provided for universal approximation theorem. It's very good. If time permits, you can go through this. Now, so we have taken this function, which is arbitrary in nature. It is not a quadratic function, or it is not a linear. It is simply an arbitrary function. What is that function? This function. Okay. So the question is, can we represent this function approximately using our sigmoid neuron? Okay. So how it is possible? It is possible like this. So this is a function which is arbitrary in nature. What is the function? I just now shown you this function. Okay. So this can be approximated using a tower function. So what is tower function? Something like this, in the rectangle shape. Okay. So this is a function that can be approximated using a tower functions. Okay. Now with a desired precision, there is some error, but that is within the desirable limits or acceptable limits. Okay. So that function can be represented using a tower functions. So Now we can approximate any arbitrary function by a sum of such tower functions. Yeah. So this function is arbitrary function is represented as a sum of these tower functions, several tower functions. Okay. Now if you observe how are the towers, they are having different heights and they have different positions. Okay. So it is starting from year to year. Now it is from year to year. So all the towers are having different heights and different positions. So sum of all these towers can approximately represent any arbitrary function with a desirable accuracy or precision. Okay. So this function can be accurately represented as a sum of the tower functions. So more the such tower functions, better the approximation. Obviously, if you take more tower function in the same gap, suppose it is from 0 to 1. So if you take more tower functions, which means if you decrease the width, obviously you get the better approximation. The accuracy increases, isn't it? Suppose you make double the number of towers. What would happen? So the accuracy will increase. More the towers, more accuracy. Okay. Okay. Now, so this is the, here I have taken more tower functions in the same gap. So you can clearly see there is a increment in the accuracy or precision compared to this function. So there is a increment in the accuracy. It is approximated in a better way compared to the previous one. Why? Because I have taken more number of such towers. Towers with different heights and different positions. Now obviously, so this function is approximated as a sum of towers. But so we need to generate these towers. How to generate? By using a tower makers. So we give input x and we have tower makers. This tower maker generates this tower maker generates this tower, so on so on. This tower maker generates this tower. Obviously, finally, so this tower maker generates this tower. We have so many towers. So if you add them here, this is the final approximation. If you add or if you sum all such towers, you get the approximation to your arbitrary function. So here the problem is how to generate these towers using a tower maker. Okay. So tower maker generates towers with different heights and different positions. So we have so many such tower makers. So if you add output of all such tower makers, you get this approximation. Okay. So before that, so we take the logistic function, which is a type of sigmoid function, which is a function of w and b. Let me write here. What is that function? Sigma of x, that is 1 by 1 plus e power minus wx plus b, where w is the weight, b is the bias. Now here the neurons are sigma neurons. Okay. Now, so we have to observe what happens if I increase the w value. The question is, what happens if I increase the w value? First of all, what is a sigma neuron? What is that logistic function? How it is? It is in this shape. So the minimum is 0, the maximum is 1, and at this value is 1 by 2. This is x. Isn't it? It is in the S shape. It is a continuous function. It is smooth function. So let us see what happens we change the as we change the value of w. Okay, so let us see now here. Yeah, so here actually this is a function of two variables, two parameters w and b. So let us see what happens if we change these two parameters. How does the function look like? So if I increase w, what is happening? It is approximately, what happened? It is approximately becoming as a step function. Isn't it? Now you can clearly see this is approximately a step function. What happened here? I have increased the w value. Actually w is indicating slope. So if I increase the slope, it becomes steep. Slope increases, it becomes maximum at particular value. If you decrease b, whatever b, it changes the position. What is this position is called? This is a point where it changes from 0 to 1. Isn't it? See, let us see. So if I change b, what is changing? The position at which the function changes from 0 to 1 is changing. You can see very clearly. B changes the position. W changes the slope. Okay. Now, so finally what I can say is, so further we can adjust the value of b to control the position on the x-axis at which the function transition from 0 to 1. Is it okay? So by changing these two values of w and b, we can make a sigmoid as an approximated step. Is it okay? So this is the how we approximate sigmoid to a step. But what is happening here? So here now, so what is this point actually? How to find this point? At this point, what is the value of the function? 1 by 2. So what is the function? F of x or sigma of x, 1 by 1 plus e power minus wx plus b. So we have to find the x at which the value of the function is 1 by 2. So this is 1 by 2. When it will become 1 by 2? Can you tell me? Solve this. So it becomes 1 by 2 when wx plus b equal to 0. Isn't it? From this equation. So what is the x value there? Minus b by w. So this is called step position, because at this value of x, our sigmoid is becoming a step. This is called step position. Is it okay? We call it as a S equal to minus b by w. Now obviously S is proportional to b and inversely proportional to w. Is it okay? It is proportional to b and it is inversely proportional to 1 by w. Now, so this is called step position. A position at which the sigmoid becomes step. You can see here. So this is how the effect of change of the parameters W and B. Now here this is the step position. So if we change these values, the step position changes. You can clearly see here. So the sigmoid is approximately becoming as a step function. So you can choose the desired step position by varying either B or W. Now this is the step position 0.40. This means minus B by W. So you can change this to any desired value. So you can clearly see that. So the step, the value at which the step changes from 0 to 1 is changing. Is it okay? No. So we are converting sigmoid again back to step because it is very easy to deal with steps rather than sigmoids. Now, but here, so to represent any function, what we need? We need towers, not the steps. But tower is just like a rectangle function. How to get rectangle from the steps? I take two step functions with different starting points, something like this. It starts at 1 minus it starts at 2. This is the step position. What is the output? This becomes a rectangle from where to where? 1 to 2. Now this is how we can generate the tower from the step function by subtracting them. Is it okay? Now you can clearly see here. So these are two approximately step functions with different step positions. If you subtract them, you get a tower. So if you can able to generate these towers, we can able to represent any continuous function, any arbitrary function. So this is how we generate towers. This is called tower maker. Okay. Now, so here, how to make towers? What is the logic? We need two sigmoid neurons. This is one, this is another one. Minimum you need 2. Okay. So if subtract them, you get the tower. Is it okay? But how it happens is, let us see. Yeah. So I have taken 2 neurons in the hidden layer. This is input X, output Y. Output neuron, input neuron. In the hidden layer, I have taken 2 neurons. Now you can see very clearly. If I change the values, you can get the tower. So the first neuron minus second neuron. Here 1.2, 1.2, minus 1.2. This is a subtraction. By changing the values, you can change the width of the tower. You can change the width of the tower and position of the tower. Like this. Okay. Like this, you can change the height of the tower. You can change height and position of the tower using this simplest neural network having 2 neurons in the hidden layer. This input layer, this output layer, this hidden layer. We are subtracting one from another. That's it. So what happens here is, so we are generating using this is X input. So using this neuron, we are generating a step. Using this neuron, we are generating another step. This is simply an addition. Here what is the weight? Plus 1 minus 1, which means we are subtracting these two. Obviously you get a tower which is just like a rectangle. This is the accumulation or addition. Like this. Input, output, two neurons, they generate step functions. If subtract one from another, you get a tower of your desired position as well as height. Okay. So, yeah, you can take more number of neurons to get more towers like this. Something like this. You're getting two towers. So, yeah, you have taken more towers. In this layer, in this hidden layer, we have a how many? 10 neurons in the hidden layer. If you take more neurons, more towers in the same gap 0 to 1. Okay. Now, so this function can be approximated with the tower functions. How? Like this. So here I have taken 10 neurons in the hidden layer. So I can generate something like this. Suppose if it is like this, what is the deviation? 2.84, high deviation. Why? Because obviously these towers are not approximating the arbitrary function. Suppose let us make it approximation like this. Now they will approximate the arbitrary function. Now you can see. So this arbitrary function can be approximated with the sum of towers. Okay. Now you can see the deviation is come down to 0.57. Is it okay? You can still decrease further by taking more number of neurons in the hidden layer. Is it okay? Now this is about the representation power of a sigmoid neuron having one hidden layer. In that hidden layer, we should have enough number of neurons. If you take more neurons, more accuracy. Why? Because you can generate more towers. If more towers, more accuracy. So that is about the representation power of a sigmoid neurons. Now the main thing is we are converting sigmoid neuron to step function by varying the parameters. That is, the step position is given by minus b by w. Is it okay? And by subtracting the steps, we can generate the tower function. So if you take more towers, more accuracy. Okay. So that is for one input, one output. You can do for what? N number of inputs and n inputs and m outputs. So for simplicity, I have explained only for single output, single input also. Is it okay? So right. So we stop here. Thank you.